Today's lecture talks about site exploration and characterization and field exploration methods. This is a topic that in a practical way kind of gets a short shrift for me, soil mechanics and foundations courses, but it's one that I'm going to come back to because to actually practice geotechnical engineering or understand how it really works, you need to understand how we do site exploration and how we then map those with boring logs and soil profiles and that kind of thing. Before we start anything, I want to show you a little video which I refer to as the boring video. It was produced about 20 years ago and in the University of California at Davis. And it gives a nice overview, a lot better than me just yammering about it at length, about soil boring methods and how they're done and what they actually look like in operation. So we're going to watch that first, and then I'm going to come back and make a few comments about that. I refer to it as the boring video for reasons that will become apparent very quickly. And then we're going to talk about some specific topics with these and how the testing methods are actually applied. So let's go ahead with the boring video.
This video presents an introduction to drilling and sampling procedures in geotechnical practice. A thorough knowledge of the tools and procedures is necessary for planning and executing an effective subsurface investigation. The extent and type of exploration depends on the specific project. For example, the design of a county road may only require explorations to a depth of 20 feet. While the design of the foundation for a high-rise may require knowledge of soil characteristics to a depth of a few hundred feet. At remote sites, all the necessary information may have to come from new soil explorations. In highly developed areas, the extent of soil exploration may be reduced based on information from the surrounding sites. The type of investigation is also greatly affected by the soil type and variability. A structure founded on a homogeneous layer of clay may require high-quality samples to accurately predict the amount and rate of settlement. But if the same structure is on soil consisting of pockets and lenses of clay, silt, and sand, information of greater value may be obtained by taking a greater number of less expensive disturbed samples to determine the location and size of these pockets and lenses. These views of alluvial sand and gravel deposits are shown to emphasize that even relatively homogeneous deposits can have complex interlayering and heterogeneity on a local scale. An appreciation of the inherent complexity of geological deposits is needed for planning or interpreting subsurface explorations. To perform an effective subsurface investigation, the project engineer must be familiar with the tools and procedures, understand the effects that drilling and sampling can have on lab and field tests, and appreciate the inherent uncertainties involved with characterizing subsurface conditions. Most subsurface investigations are performed using drill rigs of numerous types and sizes. Drill rigs can be classified into 4 basic categories: highway, off-road, over water, and portable drill rigs. Highway drill rigs, the most common, are mounted on the back of an industrial truck, allowing high mobility and minimal setup time. A highway rig is used for sites that are relatively level and easy to access. Off-road drill rigs are used when access to a site is unusually difficult. Typically, these drill rigs are either mounted on large rubber-wheeled trucks or on tracks. If an off-road drill rig cannot directly access a site, a helicopter may be used to move it into position. For soil investigations beneath bodies of water, an overwater drill rig must be used. Some overwater rigs consist of a customized barge, where the drill rig is positioned in the center and drilling takes place through a hole in the deck. Portable rigs can be partially machine operated, as shown here, or operated manually. These rigs typically have a depth limit of about 25 feet, depending on the subsurface conditions, and are used when access by an off-road rig is impossible and the expense of a helicopter is not justified. In any drilling program, the first step is to check for all possible underground utilities or obstructions, and get an underground service alert clearance as required by law. No drilling should begin without this clearance, no matter where the site is. After the drilling is completed, all boreholes or piezometer installations must be sealed in accordance with state and local regulations. Here a highway drill rig will be used to demonstrate the general features and procedures that are common to all drill rigs. After the drill rig is positioned over a borehole location, the mast is raised and secured and the drill rig is leveled. If the rig is not level, the borehole will be angled, causing great problems in drilling and sampling, in addition to producing an inaccurate soil profile. The drill head, located near the bottom of the mast, is raised and lowered using hydraulic controls. The drill head is connected to a gearbox which enables the driller to adjust the rotation speed to suit the current drilling conditions. A number of cables controlled by winches run to the top of the mast and back down to the hole. These are used for removing or attaching drill rods, auger flights, or sampling tools. Many methods of drilling have been developed, but only 4 prominent drilling methods will be discussed here. These 4 methods are solid stem continuous flight auger, hollow stem continuous flight auger, mud rotary, and coring. The main purpose of all drilling methods is to obtain representative samples of the subsurface strata at different depths. These different drilling methods are individually suited to different soil and rock conditions, and thus, more than one method may be needed on a given project. The solid stem continuous flight auger method is the simplest drilling system with only 2 basic components, the drill bit and the auger flights. The drill bit is located at the tip of the drilling stem, with the stem consisting of individual auger flights connected together. When rotating, the drill bit cuts and loosens the soil, enabling the flights to lift the soil out of the hole. Variations of the 2 most common types of bits, the finger and fishtail, are pictured here. Flights of auger are typically 5 feet long and come in outside diameters ranging from 4 inches to 14 inches. The connections between the drill bit, auger flights, and drill head use male and female connections that are secured by auger pins. The borehole is advanced by hydraulically lowering the rotating drill head as the auger and bit penetrate the soil. Flights of auger are added to the system as needed. Upon reaching a specified sampling depth, the borehole is cleared of cuttings. The augers and bit are removed by a cable. A sampling tool is then lowered down the open hole to take a sample from below the hole bottom. After sampling is completed, the bit and flights of auger are lowered back down the hole, reconnected to the drill head, and drilling is resumed. This drilling approach only works for soils where the open borehole does not collapse. Hollow stem continuous flight auger drilling is similar to the solid stem method in that the hole is advanced and soil is removed by the flights on the augers. The primary difference, as seen on the right, is that the auger flights are hollow. This allows a sample to be taken by lowering a sampler down through the hollow stem, thus eliminating the need to remove the auger from the borehole. The basic hollow stem setup is shown here. The inner bit is connected to drill rods that run through the hollow stem, and the other bit is bolted to the bottom of the lead auger. While drilling, the inner and outer bits rotate together, cutting and loosening the soil at the bottom of the hole. The soil cuttings are carried upwards by the auger flights to the top of the hole. To sample, the drill rod to cap adapter is removed, and the drill rods in the center bit are withdrawn from the hole. A sampler is then connected to the bottom of the drill rods and lowered down the hole for sampling. After sampling, the center bit is reconnected to the drill rods, lowered back down the hole, and drilling is resumed. Hollow stem augers use 2 types of connections. The auger on the right uses a 2-key connection, while the auger on the left uses an octagonal connection. Hollow stem continuous flight augers typically come in 5-foot sections, with inner diameters from 2 1/4 inches to 12 1/4 inches. The outer bit has replaceable teeth, in which rollers and cutters can be inserted to adapt the bit to different ground conditions. The common inner bits are the fishtail and stepwise bits. The main advantage of hollow stem augering over solid stem augering is that the drill rods and center bit may be removed at any time to allow for disturbed, undisturbed, or core sampling. Also, the borehole is supported by the flights of auger, eliminating any possibility of the hole collapsing. This makes it possible to drill with a hollow stem auger in sands below the water table. Mud rotary, or rotary wash drilling, is very different from the continuous flight auger methods. The underlying principle is that mud, a mixture of water and bentonite, circulates through the borehole, bringing the soil cuttings to the surface and supporting the sides of the borehole. For drilling, a bit is connected to a series of drill rods that are attached to the drill head. Drill rods typically have an outside diameter of 1 5/16 inches to 3.5 inches and are attached together using connectors like the ones shown here. Common rotary bits include drag bits, roller bits, and plug bits. The replaceable drag bit, one of the most common, consists of a barrel, bowl, blades, and connectors. This design is economical since worn teeth can be replaced rather than replacing the entire bit. The cone bit has teeth on the surfaces of cones, which rotate as the bit is turned. The spacing and size of the teeth on the cone depend on the type of material to be drilled. Plug bits come in 3 basic types: concave, pilot, and tapered. The concave plug bit, pictured here, is designed for drilling through relatively soft rock. An important difference in bits is whether they are face discharge or side discharge. Face discharge bits discharge the drilling mud straight out the end of the bit onto the bottom of the hole. This jetting action can disturb or erode the soil at the bottom of the hole. Side discharge bits discharge the drilling mud out the sides of the bit and are usually preferred because the soil at the bottom of the borehole is less disturbed. The mud is a mixture of water and bentonite, which creates a slurry with a density slightly higher than that of water. This higher density helps in the removal of cuttings, preventing them from settling on the bottom of the hole. It is important for the slurry to have the correct consistency. If it is too thick, it can clog the pump, and if it is too thin, it can leave cuttings at the bottom of a hole. The drilling mud also supports the borehole walls, and thus uncased holes can remain stable in sands below the water table. If a piezometer is going to be placed in the borehole, biodegradable products may be used instead of bentonite mud. Biodegradable products avoid the permanent sealing effects that bentonite mud has, and thus won't adversely affect the piezometer's performance. There are several components in the mud circulation system. A pump draws in the mud and sends it under pressure through the top of the drill head and down the inside of the drill rods. After it is discharged from the bit, the mud picks up the soil cuttings and carries them upwards in between the drill rod and the sides of the borehole. At the top of the hole, the mud pours out through a catch screen into a mud tank or settling basin. The mud tank has several different compartments that allow the cuttings to settle out. At the other end of the mud tank, the pump again draws the mud, which is now free of cuttings, for reuse. The drilling mud also serves as a coolant for the drill bit, preventing excess wear. It is very useful to check the cuttings as they enter the mud tank and to record any variations in the color or consistency. Such variations in the drilling mud can identify contacts between different soil strata. Operators may also detect changes in soil strata by changes in the drilling effort required to advance the hole. Sudden losses of drilling fluid can indicate that hydraulic fracturing has occurred or that a coarse free draining strata has been encountered. These types of information can supplement discrete samples and improve interpretation of subsurface stratigraphy. When mud rotary drilling in cohesionless or highly erodible soils, an outer casing is used to create a closed circulation system. Casing is advanced concurrently with drilling until it is seated in dense, unerodible soil or rock, creating a closed circulation system. A shoe, made of hardened steel, is attached to the bottom of the lead casing to prevent the casing from buckling while it is driven into the soil by the hammer. Upon reaching a desired depth for sampling, the drill bit and rods are no longer advanced. After the mud has cleared all cuttings from the hole, the drill rods are withdrawn from the borehole and the lead rod and drill bit are disconnected. The sampler is then attached to the drill rods and lowered to the bottom of the hole. After sampling, the lead rod and bit are reconnected to the drill rods to continue drilling. Generally, the mud rotary method is faster than other methods and usually results in less disturbance to the soil being sampled. This method, however, can have difficulties in gravel and cobble layers because the drilling fluid may drain freely into these layers, or the drilling process may not break up the larger particles or remove them from the hole. In the latter case, the drill bit and stem may bind in the hole. Despite these difficulties, mud rotary drilling generally works better in gravelly deposits than either solid stem or hollow stem augers. Coring of rock or very hard soils is similar to mud rotary drilling, with the exception that sampling and drilling take place concurrently. To drill and sample simultaneously, a core barrel replaces the rotary bit at the end of the drill rods. The conventional core barrel is comprised of a core barrel head, an outer barrel, an inner core recovery tube, a reaming shell, a core lifter, and a coring bit. When assembled, the coring bit is attached to the outer barrel, which is connected to the core barrel head. This section is connected to the drill rods and rotates at the same speed as the drill head. The inner barrel is connected to the core barrel head by a ball bearing connection, which allows the inner barrel to remain stationary while the outer barrel rotates. As the core barrel is rotated and lowered, the core bit cuts an annular section out of the soil or rock. This section, called the core, moves up into the inner barrel where it is protected from potential erosion by the circulating fluid. Once the inside of the core barrel is full, drilling is stopped and the core barrel is removed from the hole. By disassembling the core barrel, a continuous sample of the soil or rock is recovered. The sample is measured, identified, and stored in core boxes. After reassembly, the core barrel is lowered to the bottom of the hole and drilling and sampling are continued. Coring drill bits come in three basic types. Pictured from left to right are the diamond, carbide, and sawtooth. Diamond bits are the most versatile since they can produce high-quality cores in materials ranging from hard or very dense soil to hard rock. As shown, coring bits come in a variety of shapes and sizes, each of which is suited for a specific situation. Some systems, such as the Christensen 94 pictured here, can perform multiple tasks such as drilling, coring, and sampling. Wireline retrieval systems expedite coring by removing only the full inner barrel from the hole, thus retrieving the sample while leaving the outer barrel and drill rods down the hole. The type of coring equipment and operating procedures can greatly affect the quality of the retrieved rock cores. Rock cores can be heavily fractured and damaged by the coring process. Failure to distinguish between natural and drilling-induced fractures on the drilling logs can lead to a completely erroneous interpretation of a rock mass's characteristics. Alteration to the drilling equipment and procedures can significantly improve the core quality and percent recovery in many situations, and these changes should be recorded on the drilling logs. We will now discuss methods used to sample soils, thereby allowing the characteristics of soil at discrete points to be evaluated. The choice of sampling method depends on the intended use of the soil samples. Lab measurements of engineering properties, such as strength, stiffness, compressibility, or permeability, can be strongly affected by sample disturbance. However, time and costs increase rapidly as the degree of sample disturbance is decreased. Therefore, it may be preferable in some situations to obtain relatively inexpensive, lower quality samples during the initial exploratory drilling program. On the basis of the information obtained from such poor quality samples, the need for more elaborate sampling procedures can be judged. The split spoon sampler, also referred to as the split tube or split barrel sampler, is the most commonly used soil sampling device. The split spoon sampler is a thick-walled sampler and provides disturbed samples only. A disturbed sample contains in situ material in proper proportions, but is so disturbed that the lab test to determine engineering properties would not be representative of the in situ conditions. Disturbed samples are generally used for identification tests including visual classification, water content, grain size, and Atterberg limits. The split spoon consists of a barrel shoe, a split barrel or tube, a solid sleeve, and a sampler head. When the sharpened, hardened steel shoe and solid steel sleeve are unscrewed, The two halves of the split spoon may be separated and the sample easily removed. Generally, split spoon samplers are available with inside diameters ranging from 1 3/8 inches to 4 1/2 inches, and in standard lengths of 18 inches to 30 inches. The split spoon sampler, with an outside diameter of 2 inches and an inside diameter of 1 3/8 inches and a length of 24 inches, is the most common in practice. For sampling, the split spoon is attached to a series of drill rods and lowered to the bottom of the borehole. The top drill rod is fastened to a hammer which drives the sampler into the soil. Of the many types of hammers, the most common are variations on the drop hammer, which is manually operated, and the mechanical trip hammer. The driller lifts the drop hammer by pulling on a rope that is looped around a rotating drum, or cathead. By pulling the rope, the operator uses the friction between the rope and the cathead to pull the hammer up. The hammer is dropped by releasing the rope, thus reducing friction between the rope and the cathead. The trip hammer performs the same function, only mechanically. After the sampler is withdrawn from the borehole, the engineer disassembles the split spoon and inspects and classifies the material. The sample is then stored, such as in a sealed glass jar, and shipped to the lab for testing. If the split spoon contains two or more distinct soil types, each soil type should be stored separately, or they may get intermixed and subsequently misclassified in the lab. If there is any difficulty recovering a full sample, the split spoon may be fitted with a wire or plastic core catcher. In order to better preserve the samples, liners made of either brass, stainless steel, or plastic may be inserted into some split spoon samplers. A relatively simple and standardized method for estimating the compactness or stiffness of the soil in situ is the Standard Penetration Test, or SPT. This test consists of counting the number of blows of the hammer required to drive the split spoon sampler a specified distance into the ground. The essential features of the SPT test include a drop hammer weighing 140 pounds, falling through a height of 30 inches onto an anvil at the top of the drill rods, and a split spoon having an external diameter of 2 inches and an internal diameter of 1 3/8 inches, and a length between 18 and 30 inches. After the spoon is positioned on the bottom of the hole, the number of blows of the hammer required for 3 successive 6-inch penetrations are counted. The number of blows for the second and third 6-inch increments are added together to obtain the standard penetration resistance, or N value. The number of blows for the first 6 inches is not included in the N value, since it may be affected by disturbed soil at the bottom of the hole. It is still recorded, however, as it provides a useful check on the variability of the deposit and the consistency of the overall results. There are numerous factors that can greatly influence the N value, and thus the field engineer must pay careful attention to the manner in which the SPT test is performed. Some of these factors will now be briefly discussed. Mud rotary drilling is preferred over hollow stem augering. If hollow stem augering is used, the hollow stem must be continually filled with water or drilling fluid to an elevation above the surrounding water table. Otherwise, inward seepage of water at the bottom of the hole could loosen the soil, thereby causing N values to be unrepresentatively low. This inward seepage could also erode soil into the auger stem, which, if mistaken for the bottom of the hole, could cause N values to be unrepresentatively high. It is recommended that the diameter of the borehole be 4 to 5 inches. As the diameter of a borehole is decreased, the penetration resistance is likely to increase. Side discharge bits should be used when rotary drilling, because the jetting action of a face discharge bit disturbs the soil at the bottom of the borehole. Most drill bits can be modified to be side discharging by spot welding on baffles to deflect the drilling mud sideways. When sampling at depths less than 50 feet, A or AW drill rods with an outside diameter of 1 5/8 inches should be used. And for depths greater than 50 feet, N or NW drill rods with an outside diameter of 2 5/8 inches should be used. The heavier N or NW drill rods are recommended for the greater depths to maximize the transfer of energy from the hammer to the sampler. The split spoon sampler must have an outer diameter of 2 inches and a constant inside diameter of 1 3/8 inches. Liners may be used only in modified split spoons that maintain a constant 1 3/8 inch diameter inside the liners. If a modified split spoon with room for liners is used without them, the N values are generally 10 to 20% smaller. The amount of energy delivered to the sampler per hammer blow should be 2,520 inch-pounds, which is 60% of the theoretical maximum. The amount of energy delivered is dependent on many variables, including the type and weight of hammer, distance of free fall of the hammer, size and length of drill rods, tightness of connections, weather, and operator. If using a cat head and rope, the energy also depends on the condition and type of rope and the number of wraps around the cat head. If using a trip hammer, the energy also depends on its condition and type. The amount of energy delivered can range from 30% to 95% of the theoretical maximum. Since the N values are inversely proportional to the energy delivered, energy ratios of 30% to 95% can cause N values to vary by a factor of 3 or more. Mechanical trip hammers provide a more repeatable energy input, while the energy from drop hammers can vary as the driller becomes physically tired and slowly reduces the hammer drop height, number of blows per minute, and other variables. Thus, it is highly recommended that the energy delivered by a particular drill rig be calibrated on important projects. The blow count rate, or number of times the hammer is dropped per minute, can also affect the N value. During sampler penetration, negative or positive pore pressures may develop in the soil. A low rate of blows will permit more of the excess pore water pressure to dissipate between each blow than can occur with a faster blow rate. The result is different effective stresses and thus different N values. A rate of 30 to 40 blows per minute has been recommended. Even if these additional recommendations are incorporated in the already standardized standard penetration test, the results still only provide an indirect measure or indicator of the compactness or stiffness of the soil. Therefore, an engineer must be cautious in performing the test and analyzing the results. Thin-walled Shelby tubes are commonly used to obtain high-quality or relatively undisturbed samples. An undisturbed sample is one obtained with sampling techniques designed to preserve as closely as possible the natural structure of the material. These samples are suitable for shear, consolidation, and permeability tests, as well as for all tests performed on disturbed samples. However, a certain amount of sample disturbance is inevitable, regardless of the sampling method used, and thus the term undisturbed sample is only a relative term. Thin-walled Shelby tubes come in diameters from 2 inches to 3 inches, commonly have a length of 30 inches, and may be made of galvanized steel, stainless steel, or epoxy-coated steel. Tubes of much larger diameter can have difficulty retaining the sample. The lower driving end of a thin-walled tube is beveled to a cutting edge, creating a slight inside clearance. The upper end is attached to the drill rods using 4 hex screws and an adapter. To take a sample, a tube is attached to the bottom of the drill rods and lowered into the borehole. The sampler is then pushed downward from the bottom of the hole, a distance about 5 inches less than the length of the tube. To minimize the sample disturbance, the sampler is pushed into the ground at a high constant speed. The sampler should not be driven by a hammer, as this increases sample disturbance. After the sampler has been pushed down, the drill rods are rotated to shear the end of the sample, and the sampler is removed. Excess soil at each end of the sample tube is carefully cleaned away, and metal discs are inserted to protect the faces of the soil sample. Microfine wax is then commonly poured against the metal discs to form a seal. Alternatively, special O-ring packers may be inserted against the soil inside the ends of the tubes, and then expanded to form a seal. Tubes are then stored vertically in a padded box for transport to the lab. Some disturbance to tube samples is caused by the in situ soil being distorted as it is squeezed into the sample tube. When the empty sampler begins its downward thrust, the adhesion and friction on the outside of the tube may cause the soil to rise into the tube faster than the tube is descending. On the other hand, after the tube is partly filled, the adhesion and friction between the tube and the sample oppose the rise of the sample. Under extreme conditions, the initial portion of the sample may act as a plug, capable of displacing soft clay seams or layers so that they do not enter the sampler at all. These conditions can be greatly improved by using a piston to close the lower end of the tube until the sampler has been firmly positioned against the undisturbed soils at the bottom of the borehole. The piston is then held at this elevation, in contact with the soil, while the tube is advanced around the piston and into the soil. Initially, the presence of the piston prevents soil from rising into the tube faster than the tube's penetration rate. Later on, downward movement of the soil sample is resisted by a vacuum that develops between the piston and the top of the sample. After the sampling tube has been advanced, the piston is fixed in its new position with respect to the tube. Both elements are rotated to separate the sample from the underlying soil, and the piston and tube are removed from the hole. Piston samplers with small area ratios are capable of furnishing excellent samples of cohesive soils, even if very soft and sensitive. The necessity for a separate piston rod rising through the drill rods to the ground surface can be eliminated by using a hydraulically operated mechanism such as the Osterberg piston sampler. Thin-walled tubes generally cannot be used in very stiff or compact soils without damaging the cutting edge or buckling the tube. Even if a tube could penetrate such soils, the resulting disturbance would be excessive. Under these circumstances, the pitcher sampler, in which rock coring techniques are adapted to tube sampling techniques, may provide better samples. While the pitcher sampler is being lowered into the hole, the thin-walled tube is suspended from the cutter barrel, and drilling fluid circulates downward through the tube and flushes the cuttings from the bottom of the hole. When the tube encounters the bottom of the hole, it is pushed upward into the cutter barrel, while the circulation is diverted outside the tube into the annular space between the tube and the rotating cutter barrel. If the soil is soft, the spring at the head of the tube keeps the cutting edge of the tube below the cutter barrel, and the tube is pushed into the soil just like ordinary tube sampling. If the soil is hard, the spring is compressed until the cutting edge of the tube is forced above the bottom of the cutter barrel. As the barrel rotates, it cuts an annular ring, leaving a cylinder of soil over which the sample tube slides. The tube thus protects the sample against erosion by the circulating fluid. In this manner, the pitcher sampler adapts itself to the stiffness of the soil. From the descriptions of these sampling methods, it is clear that all samples experience disturbance. This graph shows the results of 3 consolidation tests on the same heavily over-consolidated clay. 1 block sample, 1 borehole sample, and a remolded sample. Also shown on this figure is the ideal in situ curve, or zero disturbance curve, reconstructed using Schmertmann's procedure to correct for sample disturbance effects. As shown by this typical set of data, increasing levels of sample disturbance make it progressively more difficult to evaluate the in situ compressibility of clayey soils. This graph illustrates the stress-strain behavior of 2 samples of the same very stiff clay from Oakland, California. One obtained using a pitcher sampler, and the other obtained using a modified California split-spoon sampler. The severe disturbance caused by the split-spoon sampler is illustrated by the dramatically distorted and softened stress-strain behavior, as compared to the more reasonable behavior for the pitcher sample. More importantly, it must be realized that the pitcher sample is also disturbed, and its stiffness is also likely to be considerably less than the in situ stiffness. Disturbance to soil samples does not just occur during the sampling process. Additional disturbance occurs because of the unavoidable changes in soil confining stress. During transportation of the samples from the field to the lab, or during storage at the lab, especially if significant moisture content changes, temperature changes, or tube corrosion occurs. During extrusion of the samples from the tubes prior to testing, and during handling and mounting for testing. Generally, the better the quality of the sample, the more expensive and time-consuming its recovery is likely to be. For some purposes, such as designing the foundation of a light structure on stiff clay, the expense of obtaining high-quality samples may not be justified. On the other hand, when the compressibility or shearing strength of soft clay is needed to evaluate the settlement or stability of a critical embankment or structure, even the best samples may barely be adequate. Consequently, there is a need to establish a quantitative measure of the quality of samples, especially for soft clays and silts. This video has presented a basic introduction to some of the common drilling and sampling procedures used in geotechnical practice. There are many other methods that can be used for site characterization and soil sampling, including some that are considerably more advanced than the ones shown in this video. Regardless of the method, it is important that the geotechnical engineer be familiar with the tools and procedures that are being used in the field, understand how these tools and procedures can affect the results of lab and in situ tests, and appreciate the inherent uncertainties that are involved in characterizing subsurface conditions. Primary funding for this educational research project was provided by the National Science Foundation. Additional funding was provided by the Teaching Resources Center at the University of California, Davis. Tabor consultants performed most of the drilling shown in this video. A special thanks is extended to Andy Tabor for their cooperation and support. CJ Supply graciously provided the drilling and sampling tools shown in this video. Special thanks to Bud and Alan Brodus for their cooperation and input. Valuable comments and suggestions were provided by Andy Tabor, Leslie Harder, and Michael Reamer. The assistance of Bill Sluice is also greatly appreciated. Narration by Christopher Peak and dialogue recording by Ned Jacobson.
The methods we use for in situ testing are something that have been developed over the years, and they've been codified in ASTM and AASHTO specs, and some of those are in the table you see over here on the screen. You can see that they have been, and there's a lot of documentation behind them. Interpreting them has been one of the favorite topics of research over the years, but they're very important. It's always better to use an in situ test as opposed to a laboratory test for two reasons. One of them is without the in situ test, there are no laboratory tests. In other words, without the gathering of soil, as you saw in the video, without the gathering of soil from the site, there's no laboratory test. But if you don't have to move the soil, if you can actually test it for some things in situ, which is a term we use for on the site, then you're a lot better off. And I think, and that's why in situ tests, particularly ones like the SPT and the CPT, have gotten so much, get so much discussion, and are such a large part of geotechnical engineering. The other ones not so, are not. In some cases they are. It depends on the stratigraphy and the type of soil you have. Let's start with the SPT, the standard penetration test. It goes back a long way. It's a fairly simple test. Basically, you have, and I think the boring video showed a picture of the split spoon. I remember first hearing about the split spoon during geotechnical conferences, and usually it was about lunch, and I was thinking, what's this spoon part all about? Well, basically, it's just a split tube, or split barrel, as you see in the diagram here. And basically what it is as you see, you've got 140 pound weight falling 30 inches. And that produces energy. And you drive it in at least 3, and I'm starting to see more and more 4 runs of 6 inches. You drive 6 inches, you measure the number of blows per 6 inches. You drive another 6 inches, and you measure blows for that. It takes to go from through the first 6 inches, number of blows takes to the second 6 inches, and then there's another blows to the third 6 inches. Once you get done with that, you add the 2 blow counts, and blow counts basically just the number of blows through a certain depth of soil. And from there, once you get it, you then add the last 2, and you get what is called the N value. And the N value basically is the number of blows per foot that it took to get through a foot, number of blows through a foot of soil. And you get it in a general kind of intuitive way. You think, well, the stiffer, the harder the soil, or the denser the soil, the more blows it's going to take. And that's absolutely correct, and that's why the SPT value is important. Not only that, but another fun thing is that you not only get that kind of information, but you also get a soil sample, a disturbed soil sample, and you can run Hedderberg limits and sieve analysis and classify the soil which is very valuable information, which is why the SPT test has survived in spite of its limitations. There have been several types of testers over the years, and some of those are shown. The donut, the traditional donut, which is kind of, basically a rod is used to guide the hammer down to the impact block as you raise it and drop it, to keep people's fingers from getting mashed in the block. They have what is called the safety hammer, where the hammer actually surrounds the anvil. And traditionally, usually some guy, is pulling a cat head, where usually they've got a winch. He winds the winch up, the ram goes up, it hits the top, he releases it, it drops, and I say he, most of the time it was he. And then it gets impact. Well, the problem with that is two problems. One of them was a little slow. Sometimes it varied. Sometimes he wouldn't get it to the top, and that means if you don't get a full stroke, you don't get the full energy, and your end values are iffy. There's also mechanical drag in the system. It's true with SPT equipment. We'll see that again when we get to driven piles and pile driving equipment, where on the way down you're going to get drag and you're going to get loss of efficiency problems. And to get a consistent result required a skilled operator every time. And as you're going to find out, sometimes the skill level will vary. So starting maybe about 20 years ago, we started to see more of the hydraulic hammers, which are basically, they use a hydraulic cylinder to pull the ram up and push it back down. And they're more reliable. They usually probably have energy monitoring equipment on them to monitor the efficiency. And by the way, the mechanical efficiency of an SPT hammer is let me go back. The rated energy is the 140 pounds times the 30 inches. That was if it was falling in a vacuum. The mechanical efficiency, and that translates into kinetic energy at impact, 1/2 mv squared. Mechanical efficiency is basically that energy, ideally, efficiency versus what you're actually getting. And that difference can be significant. And that's been probably one of the things that has plagued SPT tests for years, is the fact that the results have not always been consistent, and the efficiency has not, the apparent efficiency has not always been consistent. Short stroking it will give lower efficiency, lower apparent efficiency, and that sort of thing. It is even though it has many advantages, you get a soil sample out of it. It's simple. It's still the standard test in the United States, but you only get disturbed samples. The end value is a crude number, particularly with the efficiency problems. There are some soils that is not good. It's good on a wide variety of soils, but there are some which is not so hot on. And with gravelly soils, gravels in general are a problem for testing like this. And the SPT has problems with large gravel going through gravel. So over the years, we begin to realize that SPT results are not all created equal. And as a result, we need to do some corrections. So we have two levels of correction. The first level of correction is for mechanical issues. Except for efficiency. We're going to talk about efficiency next. You've got M measured there in equation 3 here on the slides is the blow count you actually get, the blow count you actually measure. And you correct it for 4 things. I'll talk about CE last. The other 3 are not as important. Therefore, borehole diameter, sampling method, and rod length. The rod length can be important because you start getting a long rod, you start getting wave effects in the rod, and the whole thing acts differently than it does under, for a shorter rod. And so that's important. Those three are fairly, easier to correct for. The one that drives everything is the energy ratio, the CE factor. The CE factor, basically, and most of this research goes back to the 1980s. In an attempt to standardize the results, basically what they started with is, let's start with what we call the assumption that the old cathead SPT was the reference standard. And at the time, it was, in terms of not only whatever reference standard they wanted to set, but it was in use, it was the reference standard. So they took it and they made 60%, and they said that, their study said that 60% efficiency is a reason. So what we're going to do, they said, was we're going to correct all the SPT values to the 60% efficient value. And that is called the N60 value. And that N60 value is shown right there. Now, CE depends. Depends on the type of hammer, and it can depend on a lot of, basically the type of hammer, how it's, with the donut and the safety hammer, the donut hammer was kind of the reference standard, but it wasn't always perfect. The safety hammer is the same way. So the generally, so they're not much help in terms of correcting them. It can be difficult, particularly if the results are old and they didn't bother to take the efficiency. The automatic hammers, the hydraulic hammers, are more consistent, and they'll run, as you see, 80-90% efficient. You can actually obviously measure that, as they say, by the ASTM standard, but they can be measured, and then you can take that efficiency and you divide it by 60 to get the CE value, and you do, and where their efficiency is in percent. And that's simply how you correct that. So let's take an example. It's an SPT reading is 20 meters below the ground surface. And the readings, the first 6 inches we had 10, the second 6 inches we had 15, and the third we had 12. And we're going to use an automatic hammer, and by some process, either by measurement, we believe that's 8% efficient. The borehole diameter is 100 millimeters, standard sampler. The rod length is at least the distance below the ground surface. It's not much longer than that, because normally, as the rig, as you saw, is at the ground level. So we want to find the N60 value. The N value is the sum of the last two 6-inch blow counts, which is 15 and 12, or 27. The first correction we're going to talk about is the energy correction factor. The efficiency of this thing is 80%, so the CE is 80 over 60, or 1.33 or 4/3. All the correction factors are unity. You can go back through. I actually show you here the other 3 correction factors. You can check those and see which one applies. And then you simply multiply the value you got, which is 27. Let's see, right here, times 1.33 times the 3 ones, and you get 36 blows per foot, or blows per 300 millimeter, either way. And that is how you get the corrected, and then you use that for the correlations. And one of the reasons why the N60, the donors, was much of the research for SPT correlations was done in the 40s, 50s, 60s, and 70s. A lot of the correlations, the ones that we use all the time, and we're going to show you some of those, a lot of those were done in that era. And when we did them in that era, nobody wants to go back and change all the correlations because it's an efficiency issue. So we just correct back to that 60% efficiency. It's not a particularly progressive way of doing it, but that's the way we do it. The last thing you want to correct for is overburden. We're going to talk about what overburden is all about when we get to effective stress, which is will be the lecture after the next one. And to correct that, we need to know what the overburden is. And I'm going to talk about how you compute that, the overburden or the effective stress, when we get to that. But I want to just show you how you correct for C sub n to get the whole thing done in one shot, so we can then proceed with something else. So let's look at an easiest way to explain that as an example. You applied after all the other corrections. You only apply that to the N60. Don't apply that to a non-N60 corrected value. So for example, and by the way, not all boring logs will tell you how their N values are corrected, or if their N values are corrected. It's not pretty, but that's the way it's done. For example, N6, usually, some boring logs will actually correct them. We'll do all the corrections or at least get them to N60, or at least give you the information so that you can get to N60. All right, let's look at this example. The N60 was 20, and the overburden pressure, the effective stress, was 2.5 KSF. You're going to find there are two sets of formulas given to you. This is one of them. The other one is in your Soils and Foundations manual book. You can use either one for this course. Eventually you'll find, if you get into this, you'll find which correlation is the better of the two. But in any event, basically the way this thing works is that the 2 in the KSF and the 100 in the KPA units, the ones over here on the right, those 2 is the atmospheric pressure in KSF. It's actually 2116 PSF, and the 100 is the atmospheric pressure in KPA approximately. And you basically divide that by your overburden, take the square root. If the value is below 2, that's it. And then if it's above 2, you stop. And you can see that coming up here to 2, and then it comes over. That's one correction. And you simply just plug and chug to get that correction. You see that right here. You got C sub n is equal to 2 over that. 2 over 2.5, take the square root, is 0.89. That's obviously less than 2. So therefore, if you've got N60 of 20 and a overburden correction of 0.89, you end up with 18 blows a foot for your N160 value, and that's pretty much the way you correct those. These are very useful for, as you see with, for example, we talk about relative density of sands. We talked about relative density before. Very loose, medium dense, and very dense. And that shows you the N60 values that correspond to those. On the other side, which is kind of more dicey than it is with sands and cohesionless soils, the N60 for clays below 2 is very soft, and then you go up over 30 is hard clays. And then you've got everything in between over here. When we say a clay is medium or stiff, or a sand is medium dense or dense, we're not just trying to blow smoke in your face. We're actually thinking about a certain type of sand with certain values, and we're going to get into more detail about how those designations can be used for standard type of values, which are very useful interpretation of soil. There are other field tests. We're going to talk about those. They're important. Particularly the CPT is important, and we're going to talk about that first. The first one is cone penetrometer test. The Dutch developed it, and I think Verrooy trumpets that fact. He pretty much rubs our face in it. So we might as well give credit where credit is due. The Dutch developed this. Originally, they developed the mechanical cone, and since that time, we've improved the instrumentation. We have the we use electronics to interpret the results. Basically, the cone test is for us. You take a probe, from a truck, which is referred to, believe it or not, as a cone truck, and then you take that and you push it in the ground. Now, the rod experiences two types of resistance. One of them is resistance at the tip, which is referred to as the tip resistance, and if you divide that there, you get the tip stress. How about that? And the area is the cross-sectional area. You don't worry about this. It's not the surface area of that cone, it's the cross-sectional area of that. You divide the force by, you get the tip stress. And then you have friction along the side of the cone, and you refer to that as sleeve friction. How about that? So those two values come out of that, and it's you can develop by just pushing it in the ground. You can get a continuous read on what's going on. One other thing that is measured with the cone is the pore water pressure. We're going to talk about how important that is when we get to effective stresses. The original was developed at the University of Delft, which is where Verrooy taught for many years, which probably explains the victory lap deal. Later on, Fugro, which is probably one of the largest geotechnical firms in the world, improved on it with the electrical cone, the piezo cone. One thing that I don't discuss in the lecture, our labs deal with it, is the dynamic cone penetrometer. And this is an important, this is kind of a combination of taking a cone and beating on it, rather like you do with the SPT. It's kind of a combination of the two. It's a very useful test to, not only, it's used mostly with pavements and that sort of thing, but it's also very useful for showing people, as a student, how cone test work and impact test work both, without having to spend on either a cone truck or an SPT drill rig. Correlations you get out of it, it's amazing. It's not it's not as easy a test to interpret as everybody thought it was, and the more people have gotten into it, the more problems. And probably the best treatment I've ever seen on overall treatment on cone is on my website. Is Bengt Felenius's Foundations book, which you can look up if you want to. You can get modulus elasticity out of it, which kind of makes sense. Undulating shear strength, you can actually get SPT correlations from CPT, or in soil classification, which is the most interesting one. There are more, basically the soil classification is done by putting two things together. The first one is the cone tip resistance, that force on the cone divided by the area. And the second is the friction ratio, and that was the y-axis. The x-axis is the friction ratio, and I kind of glossed over that here, but we'll go back. The friction ratio is equal to the sleeve friction. That's a unit. You take the area, which is the perimeter, times the length of this thing, and you take the force reading you get out of the cone, you divide by the area, you get friction. And the ratio between that unit resistance and the cone is called the friction ratio. You put those two together, and with proper interpretation, you can come up with a with a soil classification. And I'm going to show you by example. There are several different correlations of this. And Felenius discusses this. We're going to use the one from Robertson and Campanella. I think Campanella passed away here in the last couple of years. They're at the University in British Columbia. and they had extensive tests on to determine the classification. So let's get an example of this. For example, I give you a CPT result. The QC is 19.1 MPa, and the R sub F is unity. In other words, the friction ratio is 1. I could give you the F, the F value for the friction. You have to divide it to, but that's basically what this says, is that the QC and the F values are the same. Find the soil classification, soil and SPT results. And so you basically line it up like this. You've got friction ratio, and you come up. 19,000 is about here. You come out, and you're in zone 9. What does zone 9 mean? Zone 9 means it's QC over N is 5, which is a ratio between the QC and the N value. But most important, it's a sand. A couple of specialized tests that you see more in sandy soils and looser stratigraphies, marine, coastal, that kind of thing. The state of Florida is big on both of these, is the Menard pressure meter and the Marchais dilatometer. Menard pressure meter was developed in France by a gentleman named Menard. Basically what it is, it's really pretty simple. You drill a hole. By the way, you do that with that's another advantage of the cone. You don't have to drill a hole most of the time with a cone penetrometer. You don't drill a hole. You will, I guess maybe there's always exceptions there, but generally speaking, you don't. But with SPT, you do with Menard. You drill down, you lower it in the ground, and then you take some water and you expand it, and you push against the soil. Now you say the harder the soil, the higher the pressure of the water. Yeah, and that's how the Menard pressure meter basically works. There's a lot more to it than that, but that's the basic idea. And so, you can determine like at-rest pressures, and we'll talk about that with retaining walls, creep, limit pressure, and elastic modulus. Again, the Menard pressure meter can be very useful for details, and it's probably get a little bit nicer result meeting with a cone test on some of those quantities. The Italians were not to be outdone. They developed the Marchais dilatometer, and it's very similar in principle, but the difference is instead of blowing up a water balloon underground, you have a probe. And again, another thing about the dilatometer is you don't have to necessarily drill for a dilatometer test. You just shove in the ground. That blade, helps to facilitate pushing it down. It makes it easier to push down. It's kind of aerodynamic sort of thing. And then you get down there and you push out this little round little round button basically pushes out, and you can, by obviously again, the pressure the button pushes out it, and not just the pressure, but if you have take the force displacement movement of the little button, you can find out all kinds of stuff. So that's another test which you see more frequently than you used to. The last one is probably one which, for stratigraphies in this area, which are mostly cohesive, is probably more important than the vein shear test. One of the things you're going to find out is that, and I mentioned it before, is that disturbed tests are not necessarily are easier, because getting an undisturbed test out of the ground, a sample out of the ground, is not always the most straightforward thing to do. And so we have, with cohesive soils, finding out the cohesion is not always the simplest. We're going to talk about this later on. The vein shear test is, I'm going to come back to this. the vein shear is basically, you've basically got something that looks like the back end of an arrow, only instead of little feathers on the back, it's got steel plates. And you stick it in the ground and after suitable boring, and you rotate it. And again, you can use the resistance, the torque you get out of the rotation to estimate the cohesion of the sole, and we'll talk about what that means. And then you can also do a little reversing of how sensitive it is. There are some clays called sensitive clays, and they're not clays that you get easily insulted. But what they are is clays that will partially or completely liquefy under motion. And we'll talk. And they're more common in the higher latitudes. Canada, Scandinavia, Russia would see more of those. And if obviously they can be very temperamental to deal with. Any soil that changes its properties in a hurry, you got to watch for them. And those are definitely sensitive clays are definitely. And that was one of the reasons why the Swedes took the lead in developing slope stability methods, is because not only were they having problems with them just from a general geotech, but they had a lot of sensitive clays too. So the vein shear test, I am seeing more and more boring logs feature the vein shear test. It's a lot, as opposed to, we'll talk about the unconfined compression test and the triaxial, but for purely cohesive soils, if you can just determine the cohesion using the vein shear test, you're a lot better off. And I'm seeing that more often than we used to. Last topic we're going to talk about is soil boring logs. We're going to talk about them again. We're going to review them in foundation. So I'm going to give a brief overview of what they're all about. They are the most important way we communicate the nature of a site from a geotechnical standpoint to both the geotech engineers and ultimately to everybody else involved in the project. In my opinion, the lack of adequate soil borings is the most common reason problems arise in construction of foundations. The second, one other thing is they don't look at them. Is also a problem, but assuming that they're going to look at them, if you don't have the information, you can't use it. So soil boring should include quite a few things. Now, the best way to do it is to a number of things. Laboratory test results, I see those very commonly with soil boring logs. The boring logs themselves, the location, the site location map, and soil profiles as well. We'll talk about that in a minute. This is a sample boring log. This is kind of old. It has description, location of the boring and the site. Sometimes the conditions during the test, usually the site plan will show the locations of the boring. SPT, most common thing you see is SPT results. One thing you don't see on boring logs, generally speaking, is unit weights, and that's where we'll see some typical values help us out. Types of soils, most soil boring logs will include soil classification, usually unified. Ohio is the only place I know that uses AASHTO on their soil boring logs like that. And the phreatic surface, the water table, which is variable. Usually they'll make some kind of disclaimer of, well, we took this water table at this time, and they might even, if they put some kind of tube, measuring device, they might come up with, well, it moved. It's more typically in another location. That's entirely possible. That's very important. This is a slightly more detailed sort of boring log. And one of the things you'll see is there's not really there are certain conventions we see on boring logs, but there's not real hard and fast. So for example, on this boring log, the SPT are listed this way. And you see here where you've got, this says it was pushed. Yeah, this is one of those places where you have 4 SPT. Sometimes I'm seeing more of these where they take 4 6-inch runs rather than just 3. And they take an extra run or two just to get started, to make sure that the the soil is coming up into the tube properly, and that everything is seeded before they actually get to the end values. But this is in vertical column. You'll notice on this soil boring log, the SPT values are going to go this way, horizontally. You'll see that. You'll see different types of you'll see the water table locations somewhere on here. Sometimes it'll be up here. Let's see, make sure depth of water right here. Sometimes they'll put the little indicator, sometimes they won't. Again, you have to read a boring log carefully, and it's not always, it's hard to teach. It's one of those things, it's a lot easier just to do it, to learn it. One thing you'll notice at the end of this is a RQD. You get down to rock, somebody might like to know the rock quality designation. And we talked about that in the first lecture. And you'll see those on boring logs fairly frequently. In some cases, you have a boring log, you'll have more than one, where you have a rock quality up here, and then you got one there, and you got one there. So there's many different things that you can see on these boring logs. And they're arranged in different ways, but the results should be the same. CPT boring results are kind of different in that you continuously push the thing down and you get basically 3 different results. And usually the instrumentation on the cone processes a lot of stuff like dividing the areas and that sort of thing. First thing over here is the tip resistance, the unit tip resistance in TSF or KPA or MPA or whatever. The second thing is the sleeve friction. Those two can be combined to come up with the friction ratio. The last thing that's independent in this particular boring is the pour water pressure. And we're going to talk about pour water pressure more extensively when we get to the effective stress. That gives you pour water pressure. I would, and you'll see they also have the baseline pour water pressure. I'll talk about what that's all about when we get to effective stresses. But last but not least, putting this data together, you get a continuous soil classification for your site. And that's very important. It's a good, quick way of getting an idea of what's down there. 2 things which are nice to have for visualization purposes. One of them is the boring location plan. The boring location plan shows you they number the boring holes, and then they tell you where they are. For purposes of using the data, these are almost indispensable, particularly for complex projects. And you will see them on virtually plans for just about, particularly in transportation projects, you'll see them. That's almost de rigueur for boring logs to have a site plan. That's very important because sites are not uniform. Stratigraphies vary from one end to the other, from one place to another in the site. And it's important to understand that to develop a good foundation design plan. Another thing is the interpreted subsoil. Usually if you look at this, some of the boring logs will kind of line up in a row. And you can take that as a cross section and you can use it. In fact, one of the things you're seeing some of your newer geotechnical packages for generating these things, and virtually all of them are now generated by computer. It's the rare boring log that's done by hand anymore. Is the fact that each of these, you take a boring log profile like this, and these are on a line, and you can get a good idea, for example, how the bedrock or the component layer down there varies, and what other layers vary, how the water table varies, which might give an idea of is there significant water flow. So you've got all kinds of things that and those are more common. In fact, what you see a lot of is they will take the soil borings themselves, and instead of reporting them one after another, they'll take the information and they'll integrate that into a profile. So you can actually read all the soil boring information and the profile in one shot, which is very nice. Another tool in our toolbox, and we see it more often than we used to, is geophysical methods. They were developed for the oil industry. They're actually easier to apply in ours because we don't go anywhere near as deep as the oil industry did and they've used to find oil and gas. There are several types. There are basically they break down to two broad categories: acoustic methods and electromagnetic wave methods. Seismic refraction, we'll start with the first one. Basically, you use a special hammer to make a shock at one point. And then sound waves, P compression waves, you got P waves and S waves, which are important for seismic purposes, travel through the soil. And, sound travels through soil just like it does through air and water. And it's picked up at differences, and you can actually analyze these to find out the depth of the nature of the soil layers. Sometimes the instrumentation on these has improved dramatically. Most of the time, you don't do hand calculations on them anymore. They're best for if you've got one soft layer and one hard layer. If you've got intermediate layers, things get a little more complicated. They should not be used near with asphalt or concrete or frozen layers. And this is sort of a nice little diagram that shows you how they work. And the signal analysis is traditionally done using inverse methods on a computer. And you can actually get some doing it that way, you can get some fairly sophisticated profiles. P-wave velocities vary let me see if I want to put this. The denser the material, generally speaking, the higher the P-wave velocity. So steel has a higher than rocks, and then intact rocks and weathered rocks. Fissures, and of course the voids in the soil slow things down quite a bit. But you can actually, if you know what's down there, or actually you can use, it depends on how you do the data gathering, you can use that to determine what is actually down there. So this is an example, really kind of a back of the envelope example, is a seismic where actually you have you see those blue dots on here are basically locations of geophones picking up the signal from, say, ground zero or the point, the origin. And the further away you get, the longer the sound wave has to travel and the more things that it encounters. And then if it gets down to encounter layers, it bounces off that layer and comes back. And I believe we show that. Yeah, you see that with that purple line right here and that yellow line. If it's short enough, like the wave path, it goes directly, then it does like those blue and orange ones do. Whereas if it's reflected, it does like the purple and yellow ones do. And when you get to the purple and yellow point, you go that far away, you get a knee in the curve, and that's just for a simple soil profile. And then you can compute, if you know the velocities of the sonic velocities of those two layers, you can actually use this simple formula to get an estimate on how deep it is. And by the way, XC is the point at which the knee takes place, isn't it? For something a little fancier, cross-hole testing, particularly with deep foundations, basically it sends the sonic source down one hole, and it sends the sound across to another one. And you can find out what's in between them by the shear wave velocity. In fact, this is a good way to determine what the shear wave velocity actually is, by timing it between two different holes. Cross-hole testing is very useful. A kind of adaptation of that is used with drill shaft integrity, and we'll deal with that when we get to drill shafts. Downhole testing can do the same thing except with one hole and a signal from the surface. But again, if you want, it's one way of finding out what your shear wave velocity is in the soil. This is an example. It's from Colombia. By the way, both of the the soil profile you saw on the first slide and this one are both from Latin America. That one, I think they're both from Colombia. And basically, there's a lot of, geotech engineering is an international profession and is practiced by people, not necessarily, you have a lot of local geotechs and, who are familiar with those stratigraphies, but you also have specialized technologies and specialized types of foundations and whatnot where your practice is international as well. And there's a lot, and, you for your career potential need to broaden your view of where you might go and what you might do. And this is from Colombia. You see at the top, they took seismic refraction, and they developed a decent, with more modern instrumentation, they developed a decent looking profile of what the soil looked like. And then they took some other borings and they put together what they had at the bottom, which is basically the a more detailed profile of it. And they were going to build a dock over this thing. So that's what happened. That's how they did. And you see that that's a use of both seismic methods and conventional methods. Usually when they're used, the seismic method usually don't give you or any other geophysical method, don't give you the full picture. But it gives you a good start. It gives you a very good start. Ground penetrating radar is something that we're familiar with. Its biggest use is to find stuff in the ground, hard stuff in the ground. And that includes the man-made stuff. That's particularly the man-made stuff, because if you're working in an urban area and you want to start digging, you need to get some credit, because sometimes the records of whatever municipality or authority you have in terms of sewer pipes and water mains and electrical stuff ain't always the best. And this is one of the most important things about geotech in general, is that you always want, it's nice to have information, historical information. Historical information is an important part of geotechnical site planning. But it's also good to have verification of that. And ground penetrating radar for that kind of thing is fairly, even at its limits of 10 meter depth, is pretty good. Good to know that. Electric resistivity uses an electrical current. And like the other methods, it can be used to give you a profile of what's down there using electrical resistivity. And you can do it in a similar, you get similar results. Sometimes, depending on the stratigraphy, they can be better than those you get with either your sonic methods. So that, in a nutshell, is a very brief overview. We're going to come back to many of these methods as we proceed in this course in Foundations. So, until next time, thanks for watching, and God bless.